If I were to write x to the exponent of 1/2, do we know how to interpret this? What does this mean? Well, this is simply another way of writing the square root of x, right? Because there's always a little 2 written in there that we might not write, but we assume it's there, right? So the square root of x is the same as x to the 1/2. Likewise, x to the 1/3 is the same as the cube root of x, right? The cube root of x just being a number you multiply 3 times to get to x. Now, if I have something like x to the exponent 3/2, well, what that means is I have the square root of x cubed. Or in other words, another way to write this would be the square root of x, and then you cube that whole thing. It doesn't matter which way you write it. These are both going to equal each other. If I have the opposite, if I have x to the 2/3, you can probably guess what this will look like. It's the cube root of x squared, or in other words, the cubed root of x, and that's all being squared. So we want to get familiar with what this means when we have an exponent that is a fraction. We want to know how to interpret that. So some examples with some actual numbers. If you have something like 9 to the exponent of 1/2, that's the same as the square root of 9, which we all know is 3. And it's actually plus or minus 3, right? Because 3 times 3 is 9, but -3 times -3 is also 9. If you have 8 to the exponent of 1/3, that's going to equal the cube root of 8, right? The cubed root of 8 is the number you multiply 3 times to get to 8. That's 2, right? Because 2 times 2 times 2 is equal to 8. Now, it's just positive 2, right? It's not plus or minus, because if you had -2 and you multiplied it 3 times, you would get -8. So to get positive 8, you just use positive 2. Okay? Let's say you're asked to simplify r to the exponent 2/3 times s to the exponent 3, and that's all being squared, and we multiply by the square root of 20 r to the 4 s to the 5. Okay, how do we simplify this? Well, first we can change all these, radical signs, these brackets with a square. We can change it all so that every term is just to some exponent, and then maybe we can combine terms together, right? So the first thing I'll do is I'll expand this square into your bracket, which you're allowed to do, right? That's one of your exponent rules. So r to the 2/3, you multiply that exponent by the 2, so that becomes r to the 4/3. S to the 3 times 2, that's s to the 6, right? Just like that. Over here, I'm going to leave the square root 20 by itself, but I'm going to change r to the 4 square rooted as r to the 4/2, because make it over 2 because of the square root, and 4/2 we can simplify to just 2, right? So just r squared. S to the 5, that's going to become s to the 5/2, just like that. Now we can combine terms together, because if you recall, when you multiply terms together that have the same base, you just have to add the exponents. So r to the 4/3, I can just add 2, like that. S, you'll have 6 plus 5/2. And then square root 20, I'm going to start simplifying that, so I'll do 4 times 5, right? If you recall how we simplify radicals, you just split it up into 2 factors where one of them is a square, right? You can take the square root of it. That's the idea. Go check out that video if you need a review on that. From here, we want to add these exponents together, so you just need common denominators, right? So for r, you have 4/3 plus, well, this 2, you can make it over 3 by making it 6/3, and then 6 plus 4, you'll get 10/3. So if you want to show that work, you can. And then for your s, you have 6 plus 5/2. You can turn that 6 into 12/2, and then 12 plus 5 is 17/2. And then over here, square root of 4 times square root of 5, that's just 2 times root 5. And I'm actually going to rewrite this so that the numbers are on the front and then your variables are at the end. That's the most typical way you see these answers written out, so we'll do that. Just like that. So 2 root 5, r to the 10/3, s to the 17/2. Okay, and that's it. Now let's say we're asked to evaluate some expressions. Let's say we have 81/2 256 to the exponent negative a quarter. Let's say we're asked to evaluate this. How could we evaluate this? And what does that mean? Well, it just means we want to simplify our answer, right? We want to end up with a nice clean number, not, big numbers and a fraction with an exponent. You want to clean this up as best you can if you're asked to evaluate. So how do we do that? Well, first let's look at this exponent, and we notice that there's a negative, right? Well, when you have a negative exponent, that means that you have the inverse of this fraction, or in other words, you have the opposite, right? You flip it. So you can change that exponent to a positive by flipping this exponent, or by flipping this fraction. So 256 over 81 to the exponent of positive a quarter. So we just got rid of that negative. Okay, so that's progress. What do we do next? Well, next you just apply this 1/4 exponent to the numerator and to the denominator. So you're taking the fourth root, essentially, of each of these numbers. That's what it means to raise to the exponent of a quarter. So what's the fourth root? Well, that's just a number that you multiply 4 times to get each of these. You can either use your calculator, or you can recall if you're familiar with what these numbers are, but if you're not, of course, just use your calculator. So the fourth root of 256 is 4, because 4 times 4 times 4 times 4 is 256. And for 81, it's going to be 3, because 3 times 3 is 9, times itself, you get to 81. So 3 times 3 times 3 times 3 is 81. So 4/3 is going to be your final answer. Let's do another one. Let's say you have 256 to the exponent 4 over 7 divided by 2 to the exponent 4 over 7. So this one's a little different, right? Because this example on the left we just did, we had to bring an exponent into the bracket to apply to the numerator and denominator. For this example, it's already placed on the numerator and denominator. And the problem we seem to have here is that, do you want to do 2 to the exponent 4 and then take the 7th root? I don't know if you do, because it doesn't seem like you're going to really be able to figure out what that is, right? It's not going to be a whole number. So what can I do here? Well, you have some options, right? And one option would be to take that 4/7 out, right? So the opposite of what we did in the last question. So you could have 256 over 2 to the exponent 4 over 7. 256 over 2 is 128 to the 4 over 7. And then you can choose which one of these you want to apply first. Do you want to raise this to the exponent 4, or do you want to raise this to the exponent 1/7, right? I think maybe you want to do the 1/7 first, because that's going to give you a nice small number. So you do the 1/7 first and then the 4. And you're allowed to split it up like this, because when you're raised to an exponent here, and you're inside a bracket and there's an exponent on the outside, they just multiply together. So you can also go the other way and split it up like I've done here. So 128 to the 1/7, that's the 7th root. That answer is just 2. So you're left with 2 to the 4, right? And 2 to the 4 is equal to 16. So 16 is your final answer. Okay, that's one method. And for most of these questions, there's going to be several methods, right? There's several techniques you can use to get to your answer, and whatever you choose to use is perfectly okay. Another way to do this would be rewriting 256 as having a base of 2. And then because you have 2 to the exponent of something over 2 to the exponent something, your answer would be 2 to the exponent. Just subtract those exponents, and you would end up getting the same answer at the end. So go ahead and try to give it a go that way, right? Try to rewrite 256 as a number with a base of 2, so 2 to the something, and try to sort out a solution, right? And see if you get the same answer. Okay, let's go on to another one. Let's say I have 6 to the exponent of a half times the 5th root of 6 cubed. How do we evaluate this? Well, 6 to the 1/2 is just 6 to the 1/2. And this term here, I kind of want to rewrite this so that it's just 6 to the exponent of something. So you have the 5th root, and it's raised to the exponent 3. That's just going to be 3 over 5. Okay? Meaning we can just add those exponents together, right? So you get 6 to the exponent 1/2 plus 3/5, right? Your exponent rules that we learned back in grade 9, right? Now you need a common denominator. So you'll have 6 to the exponent. We can use a common denominator of 10. So like 5 over 10 plus 6 over 10. And you get 6 to the exponent 11 over 10. And I'd leave your answer like that. You can try to figure out what it is, but it'll probably be some ugly answer, right? So just leave it like that. All right, let's do another one. And this one's going to look a little bit different. Let's say we're given 10 times 9 to the exponent t over 2 plus 2 times 5 to the exponent 3t. And let's say we're asked to write this expression in the form a times b to the exponent t. So I want to change the form that this is written in, because right now it's written as, so you have like an a value here, just like you have here, right? It's just a number on the front. And then, this 9 kind of looks like your b, because it's being raised to an exponent. But then that exponent isn't just t, it's t over 2 plus 2. And then you're also multiplying by another number over here that kind of looks like b, because it's also raised to an exponent. So the form we currently have is really messy, and we want to simplify it to be in a nice form like this. A number times a number to the t. That's all, right? That's all we want to look like. So how can we do that? How can I start tearing this thing apart? Well, one thing you can do is you can look at the second term here, and you can notice that the exponent is something plus something. And we know that you're able to add exponents when you're multiplying things with the same base, right? And so we can kind of work backwards and say that must be equal to 9 to the t over 2 times 9 squared, right? Because if I was multiplying these, I would add the exponents. So basically what I have here, so I'm just working backwards, right? I'm working backwards to this, okay? And then that's times 5 to the 3t. Okay, what's next? Well, I could figure out what 9 squared is, right? 9 squared is 81, and 81 times 10 is 810. So just put 810 at the front like that. Okay, what am I left with? Well, you have 9 to the exponent t over 2. You can split that up, so it's 9 to the 1/2 to the exponent t. Same with this 5, right? You could say it's 5 cubed to the exponent t. And then you can simplify what those numbers are, right? So you get 810 times, that's just 3 to the t, right? 9 to the 1/2 is 3, you're square rooting 9. And then 5 to the exponent 3 is 125 to the t. So I think we're getting closer, right? Our goal is to have an exponent that's just t, and our exponents so far have turned into just t, right? After looking kind of complicated initially. So we're making progress, but we only want there to be one t, right? We don't want something to the t times something to the t. We just want one term to the exponent t. So how can we do that? Well, if you recall, another exponent rule says that if you have two numbers being multiplied in a bracket, you can bring the exponent into the bracket on each term, right? So kind of going backwards, right? So if I have 3 times 125 to the t, we know that we could simplify it to this, but we can also go the other way, right? We can turn this into this. So you do that. So we're almost there, we're almost done. All you have to do now is actually multiply that 3 times 125, and that's going to be 375 to the t. Now this looks a lot like the form a times b to the t, right? Some number times some number to the t. And now you're done, right? So this would be your final answer. So that's kind of a cool question that I've seen floating around the internet that I think is pretty good. And you might see something like that in your homework as well, maybe on a test. So definitely practice this question. And we're actually going to do another one, very similar to that, where we kind of do the opposite. We're given 1 over 32 times 2 to the t. So this one's not too complex, but we want to write it in the form a times b to the exponent t over 10 minus 1. So the exponent here is kind of simple, but we're going to make it kind of complex, right? So we're kind of doing the opposite of the last question. So how could I do this? Well, I'm going to start just by writing 1 over 32 times, 2 to the exponent t. Now I want that t to be over 10, right? So I can put it over 10, but if I do that, I can't just divide by 10. You'd also have to multiply by 10. So it's like you didn't really change anything, right? Because if you multiply by 10, divide by 10, you didn't change anything. So if you want to divide by 10, that 10 also has to be there. So that's the first thing I'm going to do. But then I'm going to move that 10, this 10 here. I'm going to get rid of it, right? Because we don't want it there at the end of the day. I'm going to get rid of it by writing the following. And hopefully this makes sense what I'm doing. Instead of doing t over 10 times 10, I recognize that if you have something to an exponent to another exponent, those two can multiply together. And so if I was to simplify this, I would get to this. So that means you can also go this way, right, and split that exponent up. And what's nice about that is now your exponent's just t to the 10, right? This is something I can solve, and then I'll just have a number there. So 2 to the 10, that's just going to be 1 over 32 times 1024 to the exponent t over 10. So I've successfully changed my exponent from t to t over 10. So I'm making progress. Now, I also want there to be a minus 1, right? But I can't just subtract 1. I'm not allowed to just add or subtract numbers. You can't do that. So if I subtract 1, I also have to add 1, like that. Okay? So now, just like the last operation I did, I want to get rid of this plus 1 now, because I just want this part, right? I just want that in my exponent. So how do I get rid of that plus 1? Well, again, let's recall that if you have an exponent with two things added, that just means you have that base with those exponents multiplied. And if that's a lot to imagine, let me show you what I mean. 1024 to the t over 10 minus 1 times 1024 to the exponent of 1. Because if you multiply these together, you add the exponents and you would get this, right? So I'm just splitting it up. I'm going the other way. And now you can say 1024. You can put that with your 32, right? So 1024 divided by 32, that's actually equal to 32. Pretty cool. And then 1024 to the t over 10 minus 1. And this looks a lot like a times b to the exponent t over 10 minus 1. We got it in the exact form that we wanted, right? So your a is 32, your b is 1024, and the exponent looks exactly like we want it. Okay, let's look at something else now. Let's say I have 26 to the exponent 9x plus 3, and that's equal to 1. How can I solve for x? This is tricky, right? We're solving for something in the exponent. How should we go about this? Well, the first thing I'll do is I'll look at the right side and I'll say, can I rewrite this as a base of 26? Is that possible? Like if 26 to the exponent 9x plus 3 is equal to, something, I can write that something as 26 to the exponent of, some exponent, and that would mean that those exponents are equal to each other, right? Like if 26 to the exponent equals 26 to some exponent, those two exponents must equal each other. Hopefully that makes sense, right? So what exponent would I put here on the right-hand side to make this whole right side equal 1, right? 26 to the what equals 1? The answer is 0, right? Any number to the 0 is equal to 1. So if 26 to the exponent 9x plus 3 equals 26 to the 0, then 9x plus 3 must equal 0. Okay, then just solve for x, right? Bring the 3 to the other side. 9x equals negative 3. Divide both sides by 9. X equals negative a third. And that's your answer. Not too bad, right? You just had to know that initial trick. Let's do another one. Let's say I have 2 to the exponent 4x plus 2 equals 64 to the exponent x minus 5. So again, I want the bases on both sides to look the same. So I'm going to leave this one as 2 to the 4x plus 2, because I can't really reduce that. But I can change 64 to having a base of 2, right? So 2 to the exponent, what gives you 64? Well, 2 to the 6. So I'm replacing 64 with 2 to the 6, and then you still have your x minus 5. The reason you do that is because now you can write 2 to the 4x plus 2 is equal to 2 to the exponent 6x minus 30. So I'm just multiplying the exponents together. And now you can say, well, if 2 to the exponent this equals 2 to the exponent this, then therefore 4x plus 2 must equal 6x minus 30, right? And then you can just go ahead and solve for x. So move your 4x to the right, move 30 to the left. 30 plus 2 equals 6x minus 4x. 32 equals 2x. X equals 16. That's your final answer. Let's do a couple more. Let's say I have 32 to the exponent x divided by 3, and that's equal to 8 to the exponent x minus 12. What should I do here? Well, I still want each base to be the same, right? Well, I can't write 32 as a base of 8, right? But I can write them both maybe as a base of 2. Like 32 is 2 to the exponent 5, and then you have x over 3. And 8 is just 2 to the exponent 3, and then x minus 12. So you're always trying to find kind of a common base that you can write each of these numbers as, right? And to remember, if you look at a number like 32 and 8, the reason I know it's 2, that just comes from experience, right? Like we know 32 is 16 times 2, and we know 16, is 4 times 4, and 4 you can obviously make out of 2's. So if you see a number like 2, 4, 8, 16, 32, 64, any number like that, you know that you can write it as a base of 2, right? So it just comes with experience in seeing these numbers. Now you can rewrite these as 2 to the exponent 5x over 3 equals 2 to the exponent 3x minus 36. Just multiply those, and therefore 5x over 3 is equal to 3x minus 36. So from here, we're just going to solve for x, multiply everything by 3, 5x equals 9x minus 108. Move the 108 over there, move the 5x over here. 108 equals 9x minus 5x, which is 4x. Divide both sides by 4. X is equal to 27. That's your final answer. One last question. We'll do 5 to the exponent 4x plus 3 divided by 25 to the exponent 9 minus x, and that's equal to 5 to the exponent 2x plus 5. Okay? So my base on the right-hand side is 5. My base on the left, well, on the top it's 5 and on the bottom is 25. But if you recall, 25 is just 5 squared. So I could change that right away, right? I could say this is 5 squared to the exponent 9 minus x, and on the top 5 to the 4x plus 3, and that's equal to 5 to the 2x plus 5. And then from there you could multiply those exponents, right? So really this exponent on the bottom, once you multiply it, is going to be 5 to the exponent 2 times 9 is 18, 2 times negative x is minus 2x, right? So what we're going to do is, once you figure that out, right, so you can say that's 18 minus 2x, so you can just replace that exponent. And then what we'll do is we'll subtract, right, because if you have something to an exponent divided by that same base to a different exponent, you just subtract the exponents, right? So your left side is just 5 to the 4x plus 3 minus 18 minus 2x, just like that. Right, and that's equal to 5 to the exponent 2x plus 5. Okay, subtract those. So 5 to the 4x plus 3 minus 18 minus, or actually that minus 2x becomes a plus because you've multiplied by negative, plus 2x equals 5 to the 2x plus 5. So now we can equate the exponents because the bases are the same. So on the right you get 2x plus 5, and on the left we can actually simplify this, right? 4x plus 2x is 6x. 3 minus 18 is negative 15. Move the 15 to the right, move the 2x to the left, you get 6x minus 2x equals 5 plus 15. So 4x equals 20, so therefore x is equal to 5. Okay, and that's it. That's your final answer.